So now we know that if we have two objects that have a mass, they will experience a universal force of gravity that is calculated as capital G mass 1 mass 2 over r squared. Now we know that what is happening with the object as they are moving into a circle is that force net is perpendicular to the velocity, and this is the reason why, or the condition to have a object moving into a circle. And even though that planets are not moving into a proper circle, but are moving into an elliptical shape, and we'll talk about that in a second, still this rule applies. So we know now that centripetal force is a force that steals the identity of force net. So on the other hand, what we know is that centripetal force is equal to mass velocity squared over r. You can go further and say 4 pi squared r over t squared, or mass 4 pi squared r f squared. So now, since the planets are moving into an elliptical shape, but we can easily say that it's a kind of a circle, because what ellipse is actually a deformed circle, so it is pretty much a circle. Then we can say that the force of gravity is equal to the centripetal force, meaning that centripetal force is stealing the identity of universal force of gravity. So then we will have capital G, mass of the source times mass of the satellite that is moving around that source, and that source may be the sun, if we are talking about, okay, what is the speed that the Earth is moving, so whatever is the source, or you may have a satellite of the Earth, and on that case, Earth will be the source, over r squared is equal to mass of the object that is moving, which is the satellite, times v squared over r. Okay, so now on this relationship, mass of the satellite is canceled out, is the same. So then we have, and one of the radius is canceled out. So then we have a relationship saying G mass of the source over r is equal to v squared. From here, we can find that v is the square root of G mass of the source over r. So again, on this case, we have, on the example that we see here, we have a satellite that is orbiting Saturn. Therefore, Saturn will be the source. And the radius of the orbit, which takes into the consideration from the center of the Saturn to the satellite, is 6.43 times 10 to the power of 7. And G is the universal gravity. In our case, having a radius, or this is 6.67 times 10 to the power of negative 11 times, the radius here is 6.43 times 10 to the power of 7. Oops, no, it's the mass of the source, which is Saturn. So we have to go to the table and figure that out. So after substituting the mass of the source, that in our case is Saturn, and the radius of the satellite, then we will have the velocity of the satellite equals to, so entering everything in the calculator, we will see that the velocity is 24,252 meters per second, which expressed into a correct sig digs will be 2.43 times 10 to the power of 1234 meters per second. Now, let's emphasize again, when you see a question like this in the quiz or on the test, or even on the diploma when you go, they are asking you A dot B C times 10 to the power of D meters per second. What do you have to record is only the digits. So on D2L, what do you have to write is only 2434. And when you have a diploma, what do you have to do is just have to write 2434 and bubble the numbers, number 2, number 4, number 3, and number 4 again. Let's take a look at the other example here. We have an artificial satellite orbiting Earth, has a speed of 7.6 times 10 to the power of 3 meters per second. How far above the Earth surface is the satellite orbiting? So in this case, what we are looking for is what is the altitude, how far from the surface to the satellite we have. So this is Earth with a certain radius. This is the center, and this is the radius of Earth. And here we have a satellite that is orbiting around the Earth. Now, what we are looking for is this distance from here to here. But based on this is what we are looking for. However, when we go with the logic that force of gravity is equal to centripetal force, capital G, mass of the Earth, mass of the satellite over r squared, this r squared is the radius of the Earth plus the distance d, is equal to mass of the satellite times v squared over r, and again it's radius of the Earth plus the altitude r d. So one r is cancelled, mass of the satellite is cancelled, then we have v is equal to the square root capital G, mass of the Earth over r. From here, well, we have to find r, not v. From here we can find that even from here, that radius is capital G, mass of the Earth over v squared. We have everything. Go to your table and figure out what is mass of the Earth. And actually mass of the Earth is on the data booklet, so find that on your data booklet and tell me what is r. Okay, so substituting the mass of the Earth, 5.98 times 10 to the power of 24, and the velocity as what was given, we will find that this distance from the center of the Earth to the satellite is 6.9 times 10 to the power of 6. However, what we know is that the radius of the Earth, from the table again, is 6.37 times 10 to the power of 6. So now this r that we found is equal to the radius of the Earth plus that d, and from here d will be whatever is the distance minus the radius of the distance that we found. minus the radius of the Earth. So this will be equals to this meters, or if we write it into correct sig digs, then we will have 5.36 times 10 to the power of 1, 2, 3, 4, 5 meters. So this is how far from the surface of the Earth the satellite is. Okay, those three are the one that are known as the Kepler's law motion of planetary motion. And they are very similar to what we have said in terms of the Newton's law. And it was that time where everyone was trying to mimic what Newton did. So everything was like, okay, what is the universal force of gravity is capital G M1 and 2, then they mimicked it even on the electrostatic and so on. So because it was a huge jump to move from the physics that it was before Newton and what Newton did at physics and the way that we see the world. Anyway, so what what the law states is that the planets are moving in the elliptical orbit, and an ellipse is something like this. So it's a deformed circle, and the ellipse has two centers. Center A and center B is usually, yeah, it's an oval. It's a deformed circle. So if you press the circle into two opposite sides, then you will see a deformed circle, which is an ellipse. And the ellipse has two centers. Now, the first law is stating that in one of those centers, the sun is placed, kind of. In one of the focuses of the ellipse, the sun exists. A straight line joins the sun to the planet. So let's suppose that I will draw a different one, a bigger one, so that we can see. So let's say that the sun is here. And then you have a planet here. Any planet. Doesn't matter what planet is it. The straight line joins the sun and the planet, sweeps out equal areas in equal time. So if the sun is traveling in its orbit for a given time, then this area here will be the same as if the sun is going to travel at the same time from this point to this point. So from this area here. So this is known as the area law. So area 1 is equal to area 2. And then the cube of the planet mean distance from the sun is proportional to the square of the period of revolution of the planet. Okay, so we will see and talk about this in a second. But this is what Kepler established in terms of the motion of the planets or motion of the satellites. So in this case, what do we have is that the distance between the moon and the Earth from the center of the moon to the center of the Earth is 3.85 times 10 to the power of 8. So now what do we have is force of gravity is equal to centripetal force. For universal force of gravity on this case will be capital G, mass of the Earth, mass of the moon, over the distance squared is equal to mass of the moon And now, since we are looking for the period, I will write the formula for the centripetal acceleration that includes the period. 4 pi r over t squared. Okay, so mass of the moon and mass of the moon is canceled out. And pay attention here. Those two radiuses do not cancel out because they are not on the same level. They are not both in the numerator nor in both in the denominator. So what do you have here is g, mass of the Earth over r squared, is equal to, oh, this is pi squared, 4 pi squared r over t squared. So then if you cross multiply the two, then you will have g, mass of the Earth, t squared over, no, not over, it's not over, equals to 4 pi squared r cubed. And this is where the formula comes from, the third law of Kepler. So g is a constant, mass of the Earth is considered to be constant, so, or mass of the sun, mass of the source in general is considered to be constant. So then we will have 4 and pi squared are constant as well. Then we will have r to the power of 3 over t to the power of 2 is equal to g, mass of the Earth, over 4 pi squared. And this is where the third law of Kepler comes from. So if you read it carefully, it's saying that the cube distance r from the sun is, and from the sun and from everywhere from the sun, is proportional to the square of the period of the revolution of a planet. So if you have, let's say, 2 satellites orbiting, let's suppose, the Earth, then r cubed over t squared for the first satellite is the same as r cubed over t squared for the second satellite, for the third, and so on. So this is constant, and what the value is capital G, mass of the source, over 4 pi squared. And now if we are dealing with the source being the Earth, then this will be Earth. If we are dealing with the source being the sun, then this will be the sun. But in general, the ratio, this ratio here, for a given source is always true. Do you have any questions? So in our case, we will have r cubed over t squared is equal to capital G, mass of the Earth, over 4 pi squared. And we are looking for, no, we are looking for the period. So then the period will be the square root of, what is this now? R cubed 4 pi squared over G, mass of the Earth. We know what R is because it's given to our question, and it is 3.85 times 10 to the power of 8. So we'll have 3.85 times 10 to the power of 8, the whole thing cubed, times 4 pi squared over 6.67 times 10 to the negative 11 times mass of the Earth. Find that in your data booklet, 5 point something. So the period will be 1.34 times 10 to the power of 6, and this is in seconds. And if it is needed to say in days or hours, then you convert that further. Now, a very similar question is this one here. At what height? So now we will look for the distance from the surface of the Earth to the satellite. Have a satellite that has an orbit of 10 hours. So again, we will go r cubed over t squared is equal to capital G mass of the Earth over 4 pi squared. And on this case, what we will look for is the radius. So will be the square with index 3 of, what is this now? G mass of the Earth over times first times t squared over 4 pi squared. And now we know everything on here. The common mistake that the students do here is they square root instead of square cube. 6.67 times 10 to the power of negative 11. Mass of the Earth, we said that is 5.98 times 10 to the power of 24. Period. Now this is 10 hours. We have to convert it into seconds. You can convert it straight here, or you can do it on a separate part of the work. So it is 10 hours times, in 1 hour we have 60 minutes, and in 1 minute we have 60 seconds. So it's 3600 to the power of 2 over 4 pi squared. Do not forget though that what you are finding here is the radius of the Earth plus the distance between the surface of the Earth and the satellite. And what the question is asking for is this one here. Okay, so the radius is 2.36 times 10 to the power of 7 meters. And this, as we said, is the radius of the Earth plus the altitude that the satellite is having. So then when we find the distance, the height from the surface of the Earth to the satellite, we will subtract 2.36 times 10 to the power of 7 from this, the radius of the Earth. And then from here, we find that D is equals to, so distance will be 1.99 times 10 to the power of 7. For the rest of the class, work on those practice questions. Don't forget that you have some assignments to complete as well. And tomorrow I will do a short review, and then we will write the 2 quizzes. Watch the videos, please.